So, good day, everybody. Also on the Zoom chat, if you can hear me, please hit me with like a thumbs up. Please message me on the chat if you can hear me. Otherwise, I'll have to fix that, but I'm going to pretend that you can for now. With that said, hello everyone. So if you remember last meeting, we started talking about like decision trees toward the end. So we're going to continue from that. So just as a quick recap, decision trees, they rely on binary decisions at each node. So well, not necessarily binary, but they rely on making a choice at each node. So you start off and you're like, okay, do I want to go this way, that way, or this way? And you keep flowing downwards until you get there. Once you get to the end of the leaf, or to the leaf, which is like the end of the tree. So once you get to the farthest bottom, that path will tell you that's where you assign your label. So that's where you make your guess at. Now, the pros of decision trees, as we said last time, they're really explainable because it's really simple to draw a decision tree out. As for the cons, and also, sorry, they require a little data preparation. Decision trees don't necessarily need things to be normalized and stuff, because if you think about a lot of other machine learning techniques, a lot of them require your data to be like nice in a certain way, so it needs to be like zero mean or like centered, is how we say it, stuff like that. Decision trees don't necessarily need all of that, so you don't need to worry about it. And then cons of them is that they become overly complex very fast. So if you have a decision tree and you say you allow it to train till its depth 100, which means it has like 100 levels, then that can obviously overfit very quickly. And also it can't easily train the best tree. And this part we will be going over very soon. In fact, next slide. And I'll illustrate why that happens. But in any case, now that we have a decision tree, the first question is, how do we train the decision tree? Well, let's start with a practical example, and I'm going to have you guys contribute here. I'll draw it on the board, but basically, can everyone see the data set? Yeah. Is it legible? Yeah. Okay, cool. Well then, based on this data set, we have a couple different attributes, and our target is playing tennis. So basically, we want to decide a 0-1 decision based on characteristics of a certain day, whether we should play tennis, and this is our training. So I'll start drawing a decision tree, but I'll let you guys go with first. So how would we start? If you remember from last time, basically we want to try to pick, we're making choices at each node, right? So we want to try to pick ways that we can separate the data. So what column should we start with first? What would you think? Outlook? Okay, sure. So I'll call Outlook. I'll say O, sure. Yeah, so we'll say O. Now, Outlook has, is that visible? Oh, Jesus Christ. Yeah, that's 3 of them. One second. I'm just trying to make sure that I can put this on the Zoom here. Okay, cool. So we've got an O here. That's for Outlook. Now, there's 3 different choices that Outlook can have, right? It has, Jesus Christ, sunny, overcast, and rainy. So let's say sunny, overcast, By the way, I write in cursive, so I'm really sorry in advance. I just can't read it. Sunny, overcast, and rain, right? Now, let's look at all 3 of the choices, right? Let's start with, let's just pick one of them. So let's start with sunny, right? Assuming that we have something sunny, how would we want to branch? And also, I'm going to like fix this because I know this is going to start getting bored. So I'll do that. But assuming that we have a data point where the outlook is sunny, what choice do we want to make from there? Which other attribute should we go for? Temperature? Okay, sure. Everyone else think temperature is a good idea? Cool. All right. So temperature, right? So okay. Temperature. Again, sorry for my mathematician handwriting. Well, temperature, it looks like it has 3 choices again. So hot, cold, or mild. So we have hot, cold, and mild. As you guys can see, this is going to get to PMS very quickly, but we'll deal with that later. So yeah, given temperature, hot, cold, and mild, let's go with hot then. So what should be the next category that we branch on? Well, we could do humidity, and maybe that'll work. Yeah, so that's the thing, right? Based on humidity, let's see. So if we have a high temperature or hot temperature, right? You can see that actually it kind of could work. You know what, I don't want to like just go straight down the line, because technically you pick the best one that you branch on, but I mean, it could work. So let's take humidity, for example. Why not? I don't really care. Humidity, which I'm going to abbreviate. What are the values for humidity? We high or normal? Lovely. Normal. Now, from there, well, the last one is wind speed, right? So it's stronger wind. So we can go with, let's say, high humidity, wind. That is not wind, but sure. That strong, weak. And if we have strong wind, what does that entail? Well, let's see. Well, we're down, sunny, high, or hot, high, whatever, right? So sunny, hot, high, strong humidity indicates do not play tennis. And we can see that, you've got one do not play tennis for that. Let's say sunny. We have a sunny, hot, high, but okay, so there's only one that's, sunny, hot, high, and strong wind speed. And in that case, it says do not play tennis, right? So we want to put a note here. Actually, I'll give it a 0. Let's say 0 equals don't play tennis. So we'll give it a 0, and that means don't play tennis. Now, if it's sunny, hot, high humidity, and it's a weak wind speed, well, we still don't want to play tennis. So, well, yeah, we still don't want to play tennis. So let's give it another 0, right? Now, what we can see here, actually, no, we'll talk about that. Sorry. So then let's go against humidity, if it's normal humidity, right? Well, again, we've gone through outlook, temperature, humidity, so wind, again, that handwriting, but we'll deal with that later. If the wind is strong, we have, well, it's sunny, it's hot, it's normal humidity, so that doesn't exist in the data set. It appears. Yeah. That doesn't exist in the data set. So it turns out this node doesn't even matter. And we can erase that out, right? And the reason that we're erasing it is because there's nothing like that in the data set, right? So we can't really like train and classify. Because, I mean, what do we train on, right? It's like trying to train on something that has no data for it. We can't do it. So then, okay, so we have to step back a bit, right? And if you guys have taken 132, you'll remember this as depth, kind of depth traversal-ish. Not necessarily how the algorithm works, we're just doing this for that, but it's fun. So again, we've gone through outlook and temperature. Which should we go here for cold temperature? Should we go for humidity? Should we go for wind speed? Which attribute do you think we should go for? Yeah, you don't have to do the same order every time. Like we could have started with humidity and then gone to whatever order you want. You don't have to go left. Yeah. No, that's fine. You just can't use something you've already used. That's all. So, what should we use? Should we use humidity? Should we use wind speed? Wind? Okay, cool. So, we'll go with wind. Right? So, wind can be strong, wind can be weak. What? Is it also allows not include things? Well, yeah, but that's sort of something you can do after that. We're starting with just trying to train the tree, and then as we look through it, we can always say, okay, this branch doesn't work. Right? So let's see, wind speed, if it's strong. So we have outlook strong, temperature cold, strong wind speed. Well, we only have humidity left, right? So that's humidity, I'm going to abbreviate it again. Humidity can be high or it can be normal. So if we have, so outlook is sunny, cold temperature, strong wind, and high humidity. So sunny, cool. Yeah, so do we have sunny, cool? We have sunny, we have cool. And none of those are strong. So yeah, so we run into the same thing where no, we can't do anything like that. So that pathway gets erased, right? Because we can't go downwards anymore. So the only way we can go is we win, right? So let's say we're sunny, right? Cool. weak. Well, then we have to use humidity. Again, sorry, I forgot to write that. Right, and so humidity can be high, or it can be normal. Is this visible? It is, although it's kind of a mess, but you know, so humidity can be high or normal. Now, do we have any examples where it's sunny, cool, and you know, weak wind, but it is normal temperature? Yes, we do. We have one, right? Do we have more than one? Doesn't look like it. Okay, so we only have one, right? And that says, okay, go play tennis. So in this case, we would want to pick, sorry, I'm just doing myself. Yeah, it would be hot. So we want to assign a 1 here because, you know, when we go down this pathway, our training data tells us, okay, you want to play tennis on that day, right? So let's say that we have normal humidity then, right? Do we have an example that looks like that? Sunny, cool, normal humidity, weak wind. Yeah. Yeah, it should be. I'm stupid. Sorry. We'll pretend that doesn't exist. So now we have sunny, cool, very sunny, cool, and high. I'd be surprised because that kind of doesn't really temperature make sense, but yeah. All right, there's no sunny, cool, and high. So again, Jesus Christ, this pathway gets erased because we don't have any data for that. We can't really train anything like that, right? Now, already though, we can see that this is kind of not the optimal tree, right? We have to erase a couple pathways because we don't have data for it. And ideally, I'm not going to keep us continuing down this tree, by the way, because it's really tedious and take up too much time. But the idea is that, you know, we don't want to train something where we have to backtrack and be like, okay, we can't use this node, or okay, stuff like that. Furthermore, we can also see, right here, it's not a good node right here, right? I mean, yeah, both of them are 0, but then if there's only one choice here, we really shouldn't be having it. We really shouldn't be having this as a leap, right? This should go directly to 0. So it should just end in 0 right there, right? That can come after the fact, but the idea when we're training a decision tree is not to have to do things like that after the fact. We want to be able to start, or we want to be able to pick things that are, or we want to be able to make a good tree, basically, that doesn't have to have like too many of these weird decisions. We want to be able to split the data very well at each node. And so what you guys have seen here is what I was talking about in the last point. If you look at the last slide, you can see that I said you can't easily train the best tree, right? Now, if you think about it, there is going to be some, assuming your data is good enough, there's going to be some general idea of what the best tree is, which is, you know, a tree that will always, no matter what, split the data very well and get you a good decision. This is not that tree, and in general, training such a tree is hard. It's very hard. I think the official CS terms, I think it's anti-complete or anti-hard, something like one of those two. But it's not an easy problem. And the algorithms that we choose, it's hard to consider a globally best tree because it takes a while to figure out what the best tree is. And if it takes you long to just check it, then, you know, trying to find it, then check it, find it, check it, that's going to take you eons, right? So what we did is we made locally the best choice, right? At each node, we said, okay, what's the data best? Okay, based on that, what's the data best? This isn't guaranteed to give you the best tree overall, but this is guaranteed that at each point you choose, you will pick the best choice, right? So you guys see how that means that you can't necessarily train the best tree. You're training a tree that's locally good, meaning that at each point you are making the best decision, but that doesn't necessarily mean that your overall tree is the best, right? So that's one of those cons of decision trees. Now, if you guys are interested in what the actual tree looks like, by the way, there you go, right there. We actually got close. So for all of what I said, we actually got pretty close. So, you know, stuff like that happens. But yeah, that's the ideal decision tree there. Sorry, give me a second, I need to erase this. Right. So, also credit to Professor Fauzi. Totally didn't write this from one of the classes, but you know, we'll go with it. Yeah, what's up?
One of the slides with that tree, you just have to go with the tree.
Yes, so when I say NP hard, that means that if you guys have ever heard of the Millennium Prize problems, one of them is showing P equals NP, right? That basically means that the set of algorithms that can be checked or verified in polynomial time is equal to the set of algorithms that can be checked in non-polynomial time. Now, what that means is basically assume that you have an input of size, right? That there's like, some numbered input, like a list of size. Well, some algorithms, to check that that input works in some way, it takes you polynomial time. It scales with like x squared, something like that. Some algorithms, it scales with e to the x or something, ridiculous. Decision trees are one of those algorithms. Now, it's an unsolved problem whether or not they're equal, so don't even worry about that part. But the main thing to note is that the problem is NP hard, meaning, or NP complete, so but one of the two. Basically, what it means is that in order to check that you have a good decision tree, that's going to take a long time. NP non-polynomial, like even the e to the x grows very fast, right? So things that take non-polynomial time to check will be very, very long. So one of those ideas is, yes, you would have to draw a bunch of different trees and figure out which is the best one. I think there are definitely other approaches, but the point is that all of them are mathematically shown to have been, to take a very, very, very long amount of time, meaning that you can't easily check what the globally best tree is. So you have to assume that your algorithm is good enough to get locally the best at each time, and assume that that's a good approximation. But that's one of the downfalls of decision trees, is that, you're assuming you have a good approximation, but you can't guarantee in, some sort of reasonable time frame that the algorithm you're choosing is the best. Right? So does everyone get that? Everyone sort of understand what we just did in terms of making a decision tree? Cool. So that's all the next slide says, is essentially you choose the attributes that can easily split the data. Now, this is very good if our data is separable, right? Separable means that if your data can be easily split by these choices. So let's say that you have like, let's take like data sets of like medicine, right? You guys don't need familiarity with medicine, but you can think like, there will be some patients that may exhibit similar symptoms, right? But one person, like, say they have a runny nose and stuff like that, it could be allergies. It could also be the flu, right? I'm not a doctor, so don't bear on me with that. It could, if you have a cough, it could be that you have like, some sort of respiratory illness, or again, you could just have allergies, right? There are multiple different things that can result in having different outputs, but you have the same like you have the same characteristics. And so that idea is where decision trees start, decision trees start to fail, right? If your data is not separable. Because if you think about it, you've gone through every single possible choice that you made, but you still cannot split the data up. You still cannot, based on any of these, you cannot say, okay, this is how I split between allergies and flu, right? Assuming that we just use that small data set I just thought. And so in those cases, decision trees won't work because, again, as I said, they cannot choose attributes that easily split the data. Furthermore, we need to limit the depth of the decision tree. Right now, if you look back here, you can see this is like a depth 3 decision, or depth 1, 2, 3, 4, 5. Mathematician, I can count, guys. Depth 5 decision tree, right? Now, you can think that I'll draw an example. Like, you can have like a decision tree that has like, it's starting to look like the factorization of like a bunch of different numbers. It can go down like very, very, very deep, right? Now, can anyone think of what the problem would be with a decision tree like this? A lot of time is one point, yes.
Is it not too general? It's not general.
Yes, that's the main thing I was getting at. A lot of time is one major factor, but deep learning takes time, so we just kind of go with it. But you are right, and it's not generalizable, right? This is what we call overfit, which means that it's fit too tightly to the training data. So if I introduced it, say an example that wasn't like the training data, or it was like slightly different, right? The attribute, the main one is always like, let's say you add some noise to this. I don't know how you can add noise to this data set, to be honest. But like in other data sets, let's say we add some noisy variables in there, right? For those who don't know what noise means, noise just means introduce a little bit of variability into your data, right? Not enough variability that should affect the output, but enough variability that it can start to like make things look a little better. And if you introduce noise, if you have really, really, really deep decision trees, I'm not even on camera. If you have really, really deep decision trees, then the issue is that you're not going to be able to, generalize to noisy data. And that's a problem because in some cases, you just have to work with noisy data. You can't really assume that your data is going to look perfect. So we usually limit the depth of our decision trees, right? Because we want to prefer simpler solutions because they are, as I said, more generalizable. They generalize better. So that's one of those things, which is we need to limit the depth, as I said. And if you want specifics, the algorithm for training it is called the ID3 algorithm, I believe. Specifics on it's a greedy algorithm. The pseudocode can be found if you take 422 or 320 or any of those classes like that. I'm not going to talk about it. It's kind of complex. In that it's not easy to just demonstrate to be like, oh yeah, this is how the training algorithm works. So look that up on your own time if you want. But that's the specifics for decision tree implementations. Now, with that said, we can generalize this, right? Why not one decision tree? Why not have a team of trees? Yeah, Mr. Beach was doing. So the idea is instead of one decision tree, why don't we make a bunch of different decision trees, right? Each of those trees will come up with a decision, and then after that, we can use some method of coalescing, right? The most popular one is called a voted random forest, or I don't know if it's called a voted random forest, but I'll call it that. Which basically means you have a bunch of different decision trees, they output a prediction, you then, they all basically vote, and you pick the one with the most votes. Some people, some of them will average things out. All of that depends on the application, because again, as I said, decision trees don't necessarily always have to be classification. We're talking about classification. Sometimes they can be regression, in which case the average may be better than just voting things. That makes sense. But it's very, very. It's a simple algorithm. It's just do this decision tree thing like 100 times instead of only doing it once. Now they are less explainable because if you think about it, it's easy to draw one decision tree, right? I just did it, but in terms of drawing 100 different decision trees, and then, if you think you're in a meeting or something, you have to explain to your boss why you use this model. It's a lot harder to demonstrate all 100 trees and actually make some sense of all that stuff. It's much easier to just do it with one tree. So you do sacrifice some interpretability, however, they perform much better, and we'll see that in the notebook very soon. Is that decision trees, random forests do have much higher performance on data sets because the added trees help to correct for some noise issues and stuff like that. But yeah, they can be they are less interpretable. So yeah, what's up?
Out of curiosity, when trees start voting, do certain trees have a more of a weight when voting? Like essentially, is everyone's voting? You
can make the electoral college out of it. So yeah, that is a thing. They have a thing called weighted voting. I don't know how the weights are decided. I'm going to be completely honest. I feel like some of that does come down to which tree, certain things. You can have them weighted vote, make a weighted vote, but just popular from what I've seen mostly, it's just it's voting itself. You can put weights on the vote. You can do whatever you want, but usually for classification tasks at least, which is what we're focusing on, you're doing your voting. You're voting just vote. So yeah, now. Implementation, very hard. No, it's not. It's just scikit-learn. As I said, there's one bullet point on the slide. It's just use scikit-learn. We'll see that very soon. But yeah. So on the note of implementation, since we're done with that, I'll first just stop quickly right here and ask: does everyone understand what we're going on about decision trees, random forest, things like that? Any questions? Yeah.
To verify, random forest is just a group of decision trees that work together to communicate.
Yep, it's in the name, forest trees. Yeah. Anything else? Nope. Okay, cool. So through the code notebook, we're going to be working on a notebook so I can show you guys how these things are implemented. I'm going to be using a semi-unorthodox data set, so it would be of your interest to pull this out if necessary. The links are in the Discord. They are in the slide, obviously. Have at it, and I'll just say once everyone's gotten their notebook up. Also, once you pull the notebook up, make a copy of it so you don't start running things on my notebook, so we can start running things side along. So just everyone's competing over things. So once you make a copy of the notebook for yourself, or if the guy next to you has a copy of the notebook and you can't be bothered to do it on your own, let me know. Just give me a look or something like that, and we will be ready to go. But yeah. And I'll give it what is it, 5:37? I'll give it till 5:40. We'll give you guys 3 minutes. But yeah. Also, if you have any difficulties, let me know.
Where can we find it?
Discord channel is linked in the announcements page. It's also, the PowerPoint is linked in that same post. So if you want to go, you can click that. Yeah. Again, remember to make a copy of it for yourself so that way you can run the code without interrupting things. But yeah. Watch that. I'll get it to. Yeah, I'll give it 2 minutes. Yeah, what's up? Oh, yeah, so to make a copy, you just file, save copy and drive, and like you click on that and it'll create a copy. You can see it'll just open it for you. It should be titled copy of blah, blah, blah. You know, if you don't have that, then you probably haven't done a copy. So, yeah. But yeah, so again, I'll just get another minute and then. I do have a clock, but I don't know if it's whatever. Once my computer clock says 5:40. Alright, clock says 5:40, so I'm gonna get going. Does anybody have any issues getting the notebook open and stuff? Alright, looks like no. So let's go for it, Mike's. So step 1, import everything. This is very, very simple. Not like Google has, it's not like Google's a. So first things first, what data set are we using? Now, you remember last time Sondra and I talked about how the best data for decision trees is something like, something like the tennis data set that we had earlier, right? Where it's like, you've got categorical things in each, you can make a choice. Those are like usually really good for at least classification. Well, I decided to screw that, and I decided to go into my own area of expertise. So we're going to be using MNIST today. Those who don't know what MNIST is, essentially, you have a, where am I on the camera? Okay, cool, this is good. You have an image, size 28. Okay. And what you do is you then take, this is one thing right here. I don't drop my fours with that normally, but you'll have an image that will look like this. It's essentially a collection of handwriting digits. So you can have like different things. So there'll be like some of them, there'll be like 3, or that's a squiggle, that's not a 3, that looks like a C. You'll have like 3s in there. There are some that will look like 0s. I know I'm just drawing numbers, but like they'll do like that. And there'll be different styles of it as well, right? So the goal is with MNIST is that, you take the group, you take some digits and you recognize what the digits are. You're able to classify from 0 to 9 what each digit is, like what a hand-drawn image of a digit is. Now, and this is already seen, like it's used a lot for, for like, any scanning barcodes and stuff like that. Anything where you can like, where you need to be able to like track a group of numbers, and this is a very useful data set for training that model there. However, the thing that we find weird is that you said that you needed a vector for decision trees. If I remember, you guys remember from last time, you said they needed a vector for decision trees, or something that's like, it's got like different categories in each cell. How does a matrix come into play? How can you deal with an image? Well, it's simple, right? Let's say that let's take a, let's take your image and let's, I don't know, do the blue. What's your favorite number? All right, thank you. 7, cool. Now, if you guys were looking at an image and say you were like, 2 years old, or like half a year old, and you didn't know what numbers were, right? If you're looking at an image, how would you like, how would you diagnose like what a 7 is? is? Or how would you classify like what a set is? What do you think are like key features?
Two lines, one like this and one.
Right, yeah, so we have the, I'll just like, hold it, but we have some like the line here, the line here. Is it just 2 lines? What else is important?
You could have 3 lines.
Well, you could have 3 lines, but then what makes it a set? Yeah, that's true. Yeah, the angle is useful, so like this angle right here is useful. I'm just gonna go circle things, competition stuff, but yeah. So I guess we sort of picked it out, right? You know, you wanna look in the top right and see, okay, there's like an angle here. You wanna look and see that there's 2 lines. You wanna ensure that they're touching here, or like close enough to touching, right? Because like, you know, I could have, well, I mean, I can have lines that are like that. That's not necessarily a 7. That could just be straight marks on the page. But, you know, you wanna be able to do things like that. Okay. Let's do a different number then. So, what's your favorite number? 1 digit number, boy. I did not specify, forgive me. 9, okay, 9, right? Now, I draw my 9s like this, right? But however, 9's a good one because some people, yeah, thank you, draw their 9s like that. I know that looks like a G, I can't really draw a 9 with a curvy thing, but some people do, right? So, the question is, we have to choose both of these, and we have to show that they are 9. So what would you say is a characteristic that's indicative of a number? Yeah?
Like you want to find something similar between the two, definitely circle.
Yeah, so this circle over here, again, I'll just like do that. This circle here is, you know, important, right? What else? Yeah? Yeah, so like this thing coming out of it, or this thing coming out of it. Anything else?
I would say like they have a straight line both of them, but like in the second one, the straight line is kind of like stops in the middle and then it curves.
Right, so we can just look at like the composition of each line. We can say like, okay, this one like goes straight and then curves, whereas this one just goes, you know, straight down, stuff like that, right? Now, this is a very common thing, right? When you're working with images, you want to find features that are indicative of something. So like, you know, say if you're classifying dogs versus cats, well, like, you know, if you want it to be a dog, droopy ears. I know some dogs don't have droopy ears, but like, you know, some dogs, well, a lot of dogs have droopy ears, so you know that could be something that a model picks up on, versus cats will have things that popped up. Cats also, I assume, have longer whiskers. I don't think dogs. Do dogs have whiskers? No, thank you. I don't want to sound like an idiot, but like, stuff like that, right? There are features that you can find that will be indicative of what's a dog versus what's a cat, right? But still, this doesn't answer the question of how does turning this in, how can you use a decision tree? Well, it's actually pretty simple. I'm gonna fix this, I'm gonna erase this one, I'm gonna just remove all these features that we're looking for, right? So let's say, again, we have a 9, right? Well, let's say that we just turn this into a vector of pixels, right? So each of these, I'm not gonna draw 28 different lines because like Jesus Christ, but like, you know, each of these images can be turned into like a grid, right? A grid of pixels. Now, we can look and we can be like, oh, okay, let's say like this patch over here. Let's say that we're looking at things in patches, right? In reality, we look at things in pixels, at least around this, but we can all, patches are valid in patch. So let's say we look at a patch, right? Let's say, okay. Yeah, kind of. So, yeah, that's what I said. It's a data set of hand-drawn images like this one. So it'll have a bunch of single-digit numbers, like 0 to 9. And the idea is to classify, you know, based on the image, classify it as a 0, 1, 2, 3, based on the number that's drawn in. Right? Sorry, was I not clear about that earlier? But no, you're good. Don't worry. When in doubt, blame me. But anyway, so let's say that we divide our image up into something like this, right? Well, let's say we scan through, right? We notice that this thing's black. Okay, this thing's got something, some curve in it. This thing's got more curve in it. This thing's completely empty. It's got a curve in it. Now I'm gonna like dot over things that have like curves in it or like, you know, something in it, right? We've got a curve here, nothing here, nothing here, nothing here. There's a line here, nothing here, and then blah, 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 right? Well, if it fires on this pixel, this pixel, this pixel, and this pixel, and this pixel, then we can basically say, okay, well, you know, think of a decision tree, right? It'll look through each pixel and be like, okay, is there nothing in here? If there's a 0 there, we go this way. If there's a 1, we go that way. And then you go to the next pixel. Is there a 0 there? Okay, we go to this. Is there nothing in there? We go this way. Is there something in there? We go the other way. And so on and so forth, right? So this matrix idea, we can just flatten this, right? It's like the way that we're doing it, the location of the pixels doesn't necessarily matter. We just need to know that there's something in, right? Because we can turn this into, you know, something that looks like this, where we have, okay, there's nothing in the first thing. Second thing, you know, there's something here. Third thing, there's something here. Fourth thing, nothing. The fifth thing, nothing. Next one, something here, and you know, so on and so forth, right? And so that's where a decision tree comes in. It'll look through and be like, okay, is there nothing? Okay, cool, we'll go this way. Is there something here? Cool, we'll go that way. Keep going down a certain path. And so that's how we will be using decision trees for this task. I felt it was important to explain because last time we talked mainly about decision trees for, you know, things like the tennis data set where we're just collecting, where it's not like an image where the structure is important, but you know, they're useful. And the good thing about it is that again, if you guys have heard of convolutional neural networks, those are harder to explain. I know they're really good at this, but they're harder to explain as like what they're doing. But as a decision tree, you can literally just say, okay, this pixel is doing this pixel is doing this, so on and so forth, and we can go through finishing it. Right? So anyway, first things first is we want to look at the distribution of the data set, right? Now, for those who don't understand what this means, essentially, one of the most important things when you are attacking any machine learning task, and hint when you're working on the project, I will probably be expecting you guys to do something like this. You want to look at the breakdown of variables, right? You can imagine that, you know, something like this is easy to collect data. It's easy to get a couple people to write down digits and then take pictures of them and so on and so forth. However, some data is a lot harder. So one of the projects I'm working on, or I worked on, we looked at, you know, skin lesions, right? Now you can imagine there are a lot more healthy people in the world than there are unhealthy people in the world, right? I'd hazard to guess that. So, I mean, it's like universal to what? So, you know, if there are more healthy people in the world, first off, it's going to be hard to find images of people with Lyme. Second of all, you can make things really specific and it will be hard. So in our data set specifically, and from talking to Dr. John Alcott at JHMI, one of the things that's hard is African American individuals with Lyme disease is hard to find, right? Now, that's a problem because our data set shouldn't perform worse just because someone's black, right? It should perform equally based on someone's skin color. However, if we have very little training data from that specific class of people, from, you know, class is a bad word in that sense, and class is a data science sense, not like, you know, trying to be like racist, I'm not. But like, you know, if you have very little data from African Americans with Lyme disease, then naturally it becomes hard to, like, you know, train and model to predict Lyme disease equally based on, you know, someone's skin. So the first thing whenever you have a data set is ideally break it down over, like, you know, different attributes and see what is, and see what the distribution looks like. So what we can see here is that, yeah, there's a little dip in the middle, but most or less over all of the 10 classes that we have, it's about equal, like within like 500-ish, I'd say, right? Of like, you know, the number of examples that we have for each. This is good. This is something you want because then the model has equal data for all of the classes, so it has a fair shot of training. If you don't have equal data, well then you, this is something I will talk about a lot in our performance like metrics talk next time, but if you don't have equal data, then not only is it hard to train a good model, your metrics, if you just measure simple things like accuracy, your metrics will be all wonky because you may get like 99% accuracy. But if your data is 99% of class 0, then you just predict class 0 every time and you'll get a 99%. So again, looking at the distribution of the data is important for informing which model you choose and also like what sort of performance metrics you take.
Would you ever consider splitting it into two trees based on the different class of the true? So then when you would input, then if you would ever need to know based on other trees that category?
Well, maybe, I mean, it depends, right? So if you have,
You would have something that says what category this is in, and if it's in this category, use this tree, if it's in this category, use that tree.
well, so are you saying like if you have like 9 labels partitioned down into 2 different like sections, you're not?
I had like 90 examples of the number 9,
Mhm.
only like 10 examples of the number 6. I would have 2 trees, like one for the number 9, one for the.
Yeah, oh, yeah, I see what you're saying. Yes, that is a training tactic that's called one versus rest classifiers. Basically, you train. The thing is that kind of, I mean, that makes sense in that you can train a classifier that'll either say this is a 6 or it's something else. I don't know what else it is, but it's, it's not a 6, right? It's either a 6 or not a 6. That works. However, you have to train one for every single thing. So like, for example, in this one, you have to train, either it's a 0 or something else, it's a 1 or something else, it's a 2 or something else, a 3 or something else, a 4 or something else. And so you have 10 different trees, right? That's kind of inefficient because then you have 10 different trees for just one classification problem. And that's only to output one rate. Now we are using random forests and like you can do that, but it's not the ideal way to do things. Ideally, you want a tree that'll predict, any number from 0 to 9 and tell you what it is. Because that saves you, it saves you the amount of time it takes to run. You don't have to run through like 10 different trees, you just run through one tree to get with one of the labels. Yeah. You have a question?
Just my question is, so equal data, you mean like precision relative to one another, and that accuracy is relative to the actual thing you're measuring?
Yes, yeah. So when I'm saying equal data, I mean like, there's about the same like frequency of like zeros and nines and whatever in a data set. When you're measuring things like accuracy, simply accuracy is just number correct divided by total number of samples, right? So if you, again, as I said, if your 99% of your data is one class and you have a model that literally just outputs that class every single time, then it will get a 99% accuracy, right? Because it'll get 99% of them correct, because it'll get 99, like let's say it's 99 zeros and then 1, 1, right? And it predicts 0 every time. You'll get 99 zeros out of 100 different examples, so you'll have a 99% accuracy, right? That sounds great, but it's not great because, if you give it a 1, it's never going to predict a 1. If you give it something that's very indicative of a 1, it'll never predict that. It'll always predict 0. So that's the issue that we have is that, things like accuracy can be kind of bad metrics, but in general, you want to ensure that your data is good before you start, giving importance to things like accuracy scores, stuff like that. And I'll show you a little more about that. Again, we're having a whole talk on performance metrics and what are good ones, stuff like that. But in general, that's my little head drive on that. So, yeah, I already talked about how trees are classified. First things first is we need to transform all of the images into one-dimensional vectors. So as I was saying earlier, we have a grid of pixels, and we just want to flatten it so that each row is just right after each other. We use NumPy allows you to do that, so you just kind of do that. And you can see here that if you guys think 28 squared, not to calculate, but 28 squared is 784, right? So what we've done is we've taken a grid of 28 by 28 and turned it into 784 by 1, by just flattening all of the rows into one row, essentially. And so now we have some examples each of shape 784 by 1, which is just a vector of 1784. Now from there, we need to make the decision trees first, right? So this is the important part first right here. We've got whatever, I can't be bothered. So one of the things, the first thing we should do is we import the decision tree. So remember that, if you want to get decision trees, it's sklearn.tree. Again, as I said, we're using scikit-learn. So, sklearn is the import. sklearn.tree gives you all the trees, so you can get decision trees and stuff like that. Ensemble, so random forests are what's called an ensemble method. Ensemble, if any of you guys have done anything with music, then you know that ensemble is just performers. So ensemble is a group of classifiers that are all making choices. So random forest is an ensemble method, which means that there's multiple different classifiers involved. Specifically for random forest, multiple different trees involved. So the training, it all happens here. It's a really simple slide. It's just a really simple thing. You just input decision trees, input your decision trees. Each of them have multiple different attributes, which will be, or parameters. We'll talk about those very shortly. And you then call this fit method that just, give it the training vectors, or you give it the training data and the training labels, and it fits the classifiers to those, so it trains it, and yeah, just run those. And it's a lot. Sorry about that. But yeah, we're done. Yeah. And so then after that, again, predicting is easy. So you just give it the vectors. You don't give it labels, obviously, because when you're predicting something, you want the labels, you want to figure out what the labels are. So you make it predict things, and again, this just .predict. This function right here, we will refer to it later. It is plotting something called the diffusion matrix. I will talk about those more in detail later as different talk. For now, just trust me on this. You want them to be bright on the diagonal and dark everywhere else. And you'll see what I mean very shortly. But yeah, and we'll put the accuracy on the title, so you'll see what that means. So let's first print out the decision tree confusion matrix. So I'll show you what this thing is, right? So you see this matrix and you may be thinking, what is this sort of coloring book thing that I've got going on here? Well, the idea is, you see the axis, it says that the actual label on one side, predicted label on the other side. Basically, at each square, what you have is, okay, let's say that we're looking at, this square right here, right, which is actual label 6, predicted label 0. This means that the model has predicted that an image is of labels, what the number on this square means that out of all of the images that the model predicted as 0, right, 17 of them are actually label 6, right? And so if you look at the top, it says, okay, out of all of the things that the model predicted 0, 749 of them are actually 0, or like 98%, or 76%, sorry, I think about it. 76% of them are like actually 0, right? That's what I mean when I say you want it lit up on the diagram, right? Usually we color these based on like, darker for lower numbers, higher for lighter numbers. And the idea is that you want your model, you want it to be predicting correctly, right? So you want it to predict all of the zeros as class 0, all of the ones as class 1, all of the 2s as class 2, so on and so forth, which will make all of these things on the diagonal, all of these things on the diagonals very bright. However, when you're looking at, all of the other squares, you don't want it predicting, any 2s as zeros, or, any 5s as 0, 5s as like 1s or something like that, right? So you want those squares to be dark. So that's what that means. Also, I put the accuracy up top, in case anyone wants to look at that. It's a good thing for here, and as you can see, accuracy is not great. This is what I was saying earlier. You can use decision trees for image classification. They're not necessarily the greatest, but, in terms of an example, I figured this was good to know. So, just for reference, by the way, like a 2-layer convolutional network does like 99%. So, again, don't use decision trees for images, but demo of it, figured it's not the worst in the world. So yeah, as you can see, decision trees performing kind of crap. But let's see the random forest, right? Actually, sorry, I want to talk about one thing specifically. Is that we can see one of the harder ones is, okay, let's see what it's like messing up with. So confusion matrices allows us a really nice way of figuring out where the problems are occurring, right? So let's look for the darkest square on the diagonal. Well, we can see that the model's having trouble predicting whether or not something's a 5, right? So, get out my handy little template. I'm on the thing. Get out my handy little template. You guys are probably tired of me drawing squares today, but whatever. Let's put down 5, right? That's our dark guys. Right? Well, it's having trouble predicting 5s. Well, where could the problem be? Well, let's say that someone drew their 5, like a little sloppily, right? And it ended up like this, right? Well, that could look like a 6, right? And we can see, here's the confusion matrix. Yeah, it's having trouble interpreting 5s as 6s because you've got like things that it's predicting as 6, but they're actually 5. And there's a large number, like 15% of them. Like 50% of the 6 predictions are actually 5s, right? You can also see that, okay, well, let's say we have a 5, like that. Let's say that someone was like really bad at drawing and they did their 5 like this, right? They had like a warped top. Well, that could look like an 8. And you can see, again, things that it's predicting as 8, about 20% of the model's predictions that it predicts as 8 are actually 5s, right? And we can continue to look down this. A lot of me knowing that is just from domain experience, but you can look through and see like, okay, cool, 3s would just get messed up, things like that. But that's a good thing with confusion matrices is you can see where the model is struggling. And you can think that, okay, why would it be struggling there? Well, decision trees, as I said earlier, we're not worried about where the pixels are, right? We're just worrying about whether they're lit up or not. That is a problem because, 3s and 5s and 8s, well, there are different spatial attributes, is what it's called, right? Like, depending on where pixels are, is also as important as just what their value is. And so that ends up being the issue here is like, if I draw like a 5 versus a 3 versus like, an 8, right? You'll have very similar like patterns, or sorry, not, I wanted to put a 6, I don't know why I said 3. A 6, right? There'll be very similar patterns, right? This sort of area will be lit up, you'll have like a curve here, again, this sort of area lit up, a curve here, right? They're very similar patterns of pixels that are lit up. But the model, decision trees don't have this capability, but like, other models on the other hand, will be able to say like, okay, well, a curve is lit up here, but there's no curve here. Whereas, a decision tree just looks like, okay, there's a light, there's lights up all over this place, it's probably something with a 5, right? So that's something that's like just one of those things that why decision trees are great for images, because again, it's hard to give them like, it's more tedious to give them like spatial attributes, and we need those spatial attributes for image data. But anyway, let's see if we can improve things with a random forest, right? So as I said earlier, we're using a random forest, not just a decision tree as well. So our random forest, as we trained it, has this n estimators parameter. That means how many trees you're training. So for this random forest, we did 10 trees, very small forest. I'll say the second one default is 100, and I'll show you what 100 does like very shortly. But you can see like, okay, let's train this, let's see how it's doing. Of course, it has to do things off the page. And you can see it's a lot better, right? The accuracy is 81%. The diagonal looks a lot nicer than the previous one. You can see like, this giant void here. This one looks a lot better. And it's still having trouble with 5s. Naturally. 5s are actually one of the harder ones in this. It's like, I think 5s and 9s are usually the ones that like, models that aren't like really suited for images keep sort of fuck up with, because again, as I said, spatial attributes are needed for things like that. So you can see here that the random forest is better, but the 9s aren't there. Now, the issue here is, okay, we only have, you can see I put a max depth parameter of 5, right? It means we only have a depth 5 decision tree, right? Well, we're dealing with 28 by 28 images, right? Which means that there's 784 pixels. And we only have to make like 5 choices. Good, right? That feels like a little too simplistic, don't you think? Like here we can bring down an image to 5 choices and then pick things from there. So let's say, all right, let's say max depth. We'll go with like, I don't want to do 784 because it's a little too much, but let's go with 28, right? Let's see if that improves our decision. I'm going to have it just go through all of those. Takes a bit to train, so forgive me. Also, as you can tell, if you have deeper decision trees, it takes a bit longer to train for obvious reasons. So that's another trade-off to make. But you can see, when I deepen the decision tree, we get a lot better, right? Because it's able to make more choices. It's more specific, right? Instead of just making 5 choices to decide what an entire 784 pixel image is, we're able to make like 28 different choices, and that gives us better, better performance, right? Now there is a point where this gets to be too much. Again, if your decision tree, there's a reason I didn't go with 784 choices, right? That ends up overfit. That will become very fit to the training set, and we'll start including things that may be noisy. That will give you noisy trees. You don't want them. So you can see that, if I make it a depth, depth 28, the decision tree will start to perform better though, because we're allowing it to make more choices, which for this problem is important. And you'll see now that I think if I make a random forest, let's give it 100 estimators, maxed up to 28 again. We'll just run all these cells. You'll have to give it a sec to train. I would say there's also going to be a much longer training delay. Again, we're training 100 different trees with depth of 28. It takes a lot. So, that's why, again, computational things are important. One of the things that is hard is, making sure that your model is working within the parameters of your system. So like with research, for example, I'll talk about this for a second while this trains. But like research, for example, we're just chasing performance to make sure that models look good. And so we can show that there's progress in the task because it's not like a time critical scenario. So we train like big models on like, deeper, like huge like video GPUs and stuff like that. However, if I want to make like something that detects whether or not like, the patient has like, let's say atrial fibrillation, which is measured through your ECG wave. For those who don't know, that's just a heart rate, right? Well, let's say I want to put something like that on an Apple Watch. Those things have like heart monitors nowadays, right? Let's say I want to do that so that it'll, send a message to your doctor, go to the stationary AFib, putting them in for a screening. Well, if I have a model that takes forever to run, or it's really intensive and requires a lot of computation, it's not going to work on an Apple Watch. Apple Watches don't have NVIDIA. I mean, they have NVIDIA chips, but they don't have like, graphics cards on them. They've got like whatever the latest, like, well, not even the latest. They've got like older Qualcomm chips, right? Because you need something small to run on your wrist. So those are things to take into account. So decision trees that are like small are easy to run. They take very little time to actually like, execute the prediction. However, decision trees that are very large, they may be good in this circumstance, but you know, if you have like a delay of trying to predict what someone's, like, you know, what someone's heart rate is, that can be a problem. So you want to have something that's smaller so you can run on, like, you know, different devices without blowing the device to shreds. So anyway, not blowing it to shreds, but you know what I mean. Anyway, those are the random forest, and yeah, that's actually much better. So this is close to what you really want for MNIST. It's a simple data set. You should be able to get up to 97, 99%. Random forest with 100 estimators in depth 28, we have gotten up to 97%, as you can see. And you know, we're much better at predicting things because again, we have a lot more decisions and we're a lot more trees and we're making a lot more choices. So things end up performing. So with that, I would like to say thank you guys for coming. Next time we should be having our performance metrics, assuming that the schedule doesn't change. And yeah, I'll be around for like 7 minutes-ish for questions if anyone has any, but other than that, yeah, thank you so much. What's up? Yeah. So again, as I said, each cell tells you how many, okay. Let's say that you have like 100 of class 0, right? Oh, the code, okay. Fun. Yeah, so first things first, Seaborn's a library, it's nice. Scikit-learn has this metrics package, which you can do to get all your metrics of basic accuracy, you can get metrics right. The function here, you just need to give it true labels and predicted labels. So, you know, what your test set labels are and what the classifier predicts for your test set. These are matplotlib commands to create a figure. So it creates an array of like graphs with one row and one column. So there's, you know, one graph. With big num 2 and big size 10, those just mean things like different parts of the figure. Or those are just like different attributes for like sizing and stuff like that. Here we actually call the diffusion matrix. So this will be true labels over predicted labels, and we predict things like that. We then normalize it. Now this normalizing thing is actually important. Let's say that you can have, remember when I was talking about data imbalance earlier, you could, confusion matrices, like at least the way the scikit-learn computes it, you could end up, let's say you have 2 classes, right? You can end up with a matrix that's like 950, 10, and then like 5, and then like, I don't know, not even 10, 5. Let's call this like 2, and then let's call this like 98, right? Now, when you plot something like this with color, usually the way that they do it is like based on the cell's value, based on like the maximum value, they start making colors out of things. And so like if you just plot this straight, this cell is going to be very bright, this cell is going to be very dark, this cell is going to be very dark, and this cell is also going to be moderately dark, right? Because 98 out of 950 is a very small number. So it's going to color it moderately because it's very small compared to the maximum, right? But that's not what we want. Right? This is still very good. We're having 100 of class 1 and 98 of them are predicted correctly, then that cell should be bright as well. So we normalize it, which means we convert things to a percentage. So, you know, in this case, you basically divide by the sum of the column. So this will become 0.95, this will become 0.01, no, this is 0.5. Also, I realize I can't add because it should be 10, that should be perfect. This will become 0.05, this will become 0.02, and this will become 0.98. And so now, as you can see here, the maximum value is going to be 1. So this column and this column are going to be shaded in really brightly, whereas these two are going to be dark, right? So that's the whole idea of the normalization step. The next step is just making an annotation, right? So you see how each square is labeled? That's what this one is here. Right, this one just gets rid of, you know, sometimes you have not numbers and they're advanced like missing values. These are the zeros just for the purposes of our stuff at this moment. And this one is creating the annotation array, so basically it goes through and it grabs, it just puts into a string like, you know, the number and then the percentage, formats it all nicely. Then Seaborn.heatmap, that's what plots the image. So, you know, we plot a heat map of the normalized diffusion matrix with the annotation array as this annotation array we created. I don't know what this thing is, but you know what, we'll go with it. This says, you know, to plot the color bar so you can actually see what it means. This is our color map. You can change it to different ones. So blues is one that's popular. So the bluer a square is, the better it is, stuff like that. I like magma because there's a very big difference between bad and good. Then VMIN, I don't know what that means. I think that just means like, generally don't know what VMIN means. Don't worry about it. Ax equals ax, this is just, matplotlib stuff to show like which axis we're actually plotting on, right? And so then this sets the title to have the accuracy in it. Accuracy is computed with this accuracy split command computer. Accuracy is easy to compute, so don't really worry too much, but like, And then this sets the X and Y labels, and this just makes the layout look nice. So yeah, that's the idea of it really. It's kind of a pain. I will say matplotlib is kind of annoying if you're not familiar with it already, but yeah, that's the gist of it. I'm gonna end this recording in the Zoom meeting. But